So today's topic is Stoke's theorem, but before we start Stoke's theorem, we need some mathematical tools. So here are the tools. Let's revise them before touching the Stoke's theorem. So first is, what is partial derivative? In case this is shaky, if you have a function of two variables, like for example a function g in x and y, x square y plus 3y. A partial derivative just means differentiate with respect to one variable and treat all other variables as constants or numbers. For example, we have this function and we are taking a partial derivative with respect to x. So curl g upon curl x. Then we treat y as constant, differentiate with respect to x only. So since y is constant and 3 is constant, so differentiate after differentiation it would become 0, and this thing would become 2xy. Okay, so next we are taking partial derivative with respect to y, then treat x as constant, differentiate with respect to y. Both of these terms have y, so this becomes x square plus 3. That's it, that's the whole idea, nothing more mysterious than that. Next is, what is a vector field? Imagine at every single point in space you draw a little arrow. That collection of arrows is a vector field. We write it as a vector field equals this fxi plus fij plus fzk, where fx, fy and fz are just ordinary functions of x, y and z. That tells you the arrow's length or direction in each direction I, j and k. Example is this: we have a vector field yi cap plus xj cap. At the point 1 to 0, this becomes 2i cap plus 1j cap. An arrow pointing mostly in x direction, the arrow pointing mostly in x direction there. Okay, so what is a line integral? What is a line integral? Build this with a real tiny example. Let's see. So we have this closed integral. This C, what is this C? Thinking of walking along a path C. Okay, so this is a closed path C and we are integrating along that path, integrating vector field. At every tiny step, your displacement is a tiny vector dl. Okay, dxi plus dyj plus dzk, done. You take the dot product of the field f at that point with your tiny step dl and add all these up over the whole path. The little circle on the integral sign just means the path is closed. You end up where you started. So this fdl becomes fx dx, fy dy and fz dz. Okay, so next is, so a line integral is really just three separate ordinary integrals added together. So this becomes this thing. Keep this fact in your pocket. It's the reason the proof gets split into three pieces later. Okay. So what is curl? Curl takes a vector field and produces a new vector field defined by this formula. I'm not deriving where it comes from. Just take it as definition. It's given in your syllabus already. Let's just accept it because इसका derivation वैसे भी काफ़ी lengthy हो सकता है. So if we have a curl of a field, then we use this formula. Partial differentiation of z with respect to y minus y with respect to z for I. I के साथ x आता है ना, we don't have any x in here, we only have like z, y, y, z. Now j के साथ y आता है, we only have x, z, z, x. And k के साथ z आता है, but we have y, x, xy. So xy यहाँ पे सीधा है एक्स वाई, यहाँ उल्टा है जी एक्स, एंड यहाँ सीधा होगा एक्स वाई, ऐसे यहाँ पे उल्टा सीधा एंड उल्टा, जी वाई एक्स जी एंड वाई एक्स, ब्रैकेट के अंदर माइनस बाहर प्लस. दिस इज हाउ आई वुड ट्राई टू रिमेंबर इट एनीवे. सो ट्रिक टू रिमेंबर it, it's the determinant. Okay, so we can also like remember it this way. It's the determinant of this thing. I j k f x f y f z. This is easier, but we can also remember like this straight as well. It's not that hard. Okay, so partial differentiation with respect to x, y, and z. Okay, if you know how to expand 3 cross 3 determinant, actually I forgot how to expand. Maybe for I you like cross, cancel out these two and multiply and subtract this thing, right? Yes, I do remember, but okay, so if you know how to expand this determinant, this instantly gives the formula above. This is genuinely just bookkeeping, not new physics. Okay, this is the formula for curl. Fine. So what is surface integral and normal vector n? Take a surface S like a curved sheet floating in space. Chop it into tiny patches. Each tiny patch has an area ds, just a number like 0.001 meter square. Okay, a direction it faces a unit vector n cap perpendicular to the patch. Okay, so this double integral, is it double integral? What is this? Surface integral. तो surface होता है मतलब लेंथ क्रॉस ब्रेथ होता है ना, मतलब उसमें 2 डायमेंशनल होता है surface. So maybe that is how at least I would try to memorize this double integral. We don't have a loop, we have a surface. So S A area times n उस एरिया की डायरेक्शन एंड ds times ds. A is area, right? What is A? So we have a surface. That surface itself is area, no? This means that at each patch ds dot the field with the normal direction. Okay, this A is field with normal direction, multiply by the patch area, the sum over the whole surface, and the sum over for the whole surface. This measures how much A is flowing through the surface. Okay, vector field flowing through surface. So we add all of the small patches and we take the direction in count, because obviously if like vector field is flowing upwards and we have a tilted area straight or maybe perpendicular, then different amount of vector field is going to flow through it. So okay, it makes sense. Chain rule multi-variable version. This is the part that trips people up, so extra slow. Okay, suppose z spends on x and y. Sorry, suppose z depends on x and y, so z is a function in x and y. Now suppose fx is a function of xyz, but on the surface z itself is a function of x and y. So if you sit on the surface, fx effectively only depends on x and y. Question: if I differentiate fx with respect to y while staying on the surface, what do I get? If I differentiate fx with respect to y while staying on the surface, what do I get? There are two ways y can. This is actually a little trippy. Okay, so there are two ways y can affect fx directly. Fx has y in its formula, so its contribution we can calculate, or indirectly through z, because z also is affected by y, so depends on y, so fx depends on z. If y changes, z changes, that changes fx too. Contribution is this times this. So how much we are seeing कि y के चेंज होने से fx में कितना चेंज आता है, राइट? fx में कितना चेंज आता है, तो fx में कितना चेंज हो रहा है z के चेंज होने पे, एंड देन z में कितना चेंज हो रहा है y के चेंज होने पे. Then we are going to add these two, I guess. So the total rate of change, sum of both effects. Okay, so this plus this. Okay, now I get it. Now I get it. Thoda thoda. Okay, so concrete numerical example. So this isn't abstract. For example, we have this f of x, this function z square plus y, and suppose the surface z is also in itself a function xy. Okay, so direct route to see affects how fx is getting affected by y. We have the same condition, no? So direct route is to see directly how fx is being influenced by y by taking partial derivative with respect to y. Then this is going to be 0 and this could become 1. Okay, and then indirect rule is to see how fx is changing with respect to z. So 2z, and then multiply it with how z is changing with respect to y. So x, right? X, now 2zx. Okay, so then 2zx plus 1. This is our total effect, like how fx changes due to y. Here is how. Okay, with how fx changes with y. Check by direct substitution. Substitute z equals xy into fx first. So what we are doing is xy square, xy the whole square plus y. So x square plus x square y square plus y. Now differentiate with respect to y. It would become 2x square y plus 1. 2x square y plus 1. Okay, then what? Compare with a chain rule answer. Yes, so we have the same answer. Great, the chain rule formula works. Keep this trick in mind. We reuse it in step 4 of proof. Next, what we need is the Green's theorem 2D. Treat this as a non-imported tool. So the next formula we need to remember, first was for curl. That was like determinant form, so that was easier. Now we have this formula for a flat region A in xy plane bounded by a closed curve C. So we have a flat region in a plane, but that flat region is not a particular shape. I guess it's just a closed curve, so it can be random shape but flat. So for that we have this formula, this pdx. What is this pq? I don't know. Let's see. This is proven separately, usually in your vector calculus math methods section. We will just use it as a tool here, the same way you use this without re-deriving it every time anyways. So this is a line integral and surface integral for pdx plus qdy. Then this becomes qdx and pdy minus, and then I don't know how this works, but okay. Take a breath. Everything above is just vocabulary, nothing hard yet. Once you are comfortable with this, say continue. Okay, let's just continue. The last bit was the most difficult. I don't know how I would remember this thing. Maybe I'd have to make flashcard. I don't know. Part 2 is proving Stoke's theorem step by step. First, let's state clearly what we are proving. So, we are proving this. This is Stokes' theorem right here. Left side is walk around the boundary loop C. Add up FDL. If we are walking around a boundary loop C and we add up field for that loop, and then right side we have covered the surface S which has C as its edge, okay, with patches this ds, add up curl dotted with the normal. I don't know, I seriously don't know what the hell is going on in a strategy. From section 1.3 we know f dot dl is this, okay. So three separate pieces. We will prove the theorem is true for just fx piece alone, then repeat for fy and fz, then add all three, divide and conquer. Okay, what the hell, divide and conquer. Set up, picture the geometry first. So imagine a bowl shaped or any curved surface S, floating in 3D space described by equation z equals function of in an x and y, meaning for every xy the height z is determined. The edge of this bowl is a closed curved C living in 3D on the surface itself. So it's not a flat surface because the curve is living in 3D. Fine, so now shine a light straight down from above. The shadow of the surface S on the flat ground xy plane is a flat 2D region, call it A area. The shadow of the edge curve C is a flat 2D curve, call it C. Okay, now we turn surface area, 3D surface area to 2D surface area. This is either going to be equal or maybe less than that, and similarly this 3D edge to 2D edge under this shadow projection operation. Fine, so call for part A is prove the theorem just for fxi piece. Okay, fine, this that is we want to show this is true. Okay, so fx के लिए ठीक है, curl of fxi, go back to the full curl formula from, ठीक है, we are going to use this formula to find this curl. If we pretend fy equals to 0 and fz equals to 0 everywhere, that is we only care about fx part, every term containing fy and fz becomes 0. So this becomes 0 and this I don't know. What survives? I terms had fz and fy only, so 0, and j terms has both x survives minus fz upon x 0 survives as this only y. We pretend fy is 0 and fz is 0. Okay, so we only pretend this is 0, not like this part. So now this is 0, so this complete thing is 0. Okay, fine. Okay, and in k, let's guess k wale mein bhi only this is going to survive. Since this is 0, so this term is going to cancel out, so minus this survives. Fine, so now this curl become this, no I component at all, just j and k pieces. Keep this result, we use it in step 3. Okay, now we have this result from the curl formula. Fine, so step 2 is write nds in terms of flat dxy. It was our initial formula, so we are trying to prove this. So हमें ये वाला part मिल गया है And now we are trying to find this part, and then maybe we are going to use the surface integral formula. Let's see. So now write NDS in terms of flat dxy. This is standard geometric fact for surface z. Okay, for this proven in the surface integral part of your syllabus, we just imported another imported formula, guys. So third imported formula we need to remember for this proof. So NDS becomes this thing, z z and I don't know I j, and this is k, dx dy dx dy dx dy. It has none, it has 1, and minus minus partial derivative of z with respect to x and z with respect to y. Why does this make sense? Partial differentiate derivative with respect to z क्या होगा? Of z with respect to z is 1 or not? I don't know. Or is it 0? I don't know. Anyways, so why does this make sense intuitively? If the surface were perfectly flat and horizontal, then z is constant. This equals 0. Then z is constant. Z would not change. What is the z? I forgot. Surface. Z is the surface. If z is a surface, and where is it? If the surface were perfectly flat and horizontal, then the shadow would not change it and z would be constant. So change in z with respect to x or with respect to y is obviously going to be 0. Then NDS becomes k dx dy. The normal just points straight up. The normal just points straight up, which is obviously correct for flat horizontal sheet. The extra terms account for the surface being tilted. From this pull out just, I don't know how this means the point is going to be straight up. K to ठीक है straight up, but what do you mean ds dy? I don't know. Anyway, so from this pull out just the two pieces we need, matching step 1 which only had j and k components. From this pull out just the two pieces we need, matching step 1 with only j and k component. Okay, so since we don't have any I, we only have j and k, so we are going to take this part only. Is it? Pull out just the two pieces we need for J and K, J and DS, K and DS. एक minute. How does this happen? क्या किया है यहाँ पर सर? ये क्या हुआ है? I don't know. Step 3 is to multiply step 1 and step 2 together. Step 3 is to multiply step 1 and step 2 together. We'll see the math, but for now let's just accept the result. So we want this. So using step 1 and dotting with NDS, we get how is this happening? So we have this fx by fx z fy fx y gk jk, and we have fx z fx y j and k. Okay, NDS अंदर दोनों के साथ मल्टीप्लाई कर दिया, and then we are going to substitute NDS with j NDS and k NDS with this. Okay, get it. बट ये यहाँ पे कैसे आया? From this, pull out just the two pieces we need, matching step 1 matching step 1, which only had j and k components. So since we have j and k component only, we are taking this j dx dy, j dx dy. This is nds, j dx dy, dz upon curl z upon curl y. So curl z upon curl y माइनस का, बट ये जे कैप इधर था ना, तो ये जे कैप उधर जाके डॉट प्रोडक्ट कैसे बन गया, ये समझ नहीं आ रहा है मुझे. बस इतना सा कन्फ्यूजन है कि ये उधर कैसे जा रहा है. आई डिड नॉट अंडरस्टैंड स्टेप 2. ठीक है. आफ्टर वी सब्सटीट्यूट एंड मल्टीप्लाई, पुल डी एक्स डी वाई आउट एज कॉमन फैक्टर. सो डी एक्स डी वाई दोनों से बाहर. This becomes dx dy बाहर गया तो we have curl fx fz, curl fx fz, no, curl fx curl z times curl zy, ये माइनस होना चाहिए था ना. would we have this plus, तो साइंस चेंज कर दिया, माइनस बाहर निकाल लिया. ओके, माइनस बाहर निकाल लिया है. ठीक है. एंड देन डी एक्स डी वाई हट गया. वी हैव कर्ल एफ एक्स कर्ल एफ एक्स एल वाई. ठीक है. Pause and look at that square bracket. Does it look familiar? Go back to section 1.6. That is exactly the chain rule formula for. So now we are going to use chain rule. Fine. So replace the bracket using chain rule. Define a shorthand. Let gxy equals fx xy zxy. This just means take fx and substitute the surface equation z xy into it, so it's now purely a function of x and y. From section 1.6, where is section 1.6 now? This was the section 1.6, the chain rule. From section 1.6, this curl g upon curl y equals this thing. This is precisely the bracket in stars, so star simplifies to. Okay, so this xy xz zy xy xz zy, this is completely similar, so this simplifies to this gy dx. Okay, this is the payoff of the whole setup. A 3D curl expression has collapsed into a plain 2D partial derivative of g. Nice and clean. Integrate both sides over the surface and apply Green's theorem. भाई कितना लेंदी है ये. Integrate over the whole surface S equivalently over the shadow region A. Integrate the whole surface S equivalently over the shadow region A. Since we have converted everything to dx dy. क्या मतलब इंटीग्रेट over the whole surface S? So we are going to integrate both sides. Surface integral, and either area, is it same? Now bring in Green's theorem with choice p equals g and q equals 0. With the choice P equals Z and Q equals 0. Why? Let's use green theorem with this condition. Okay, so this becomes 0 and we are left with this. Okay, look, the right hand side here is identical to the right hand side of star star, so we can equate the left hand side. ठीक है. So we have area, double integral area, minus minus कर्ल जी कर्ल वाई कर्ल जी कर्ल वाई dx dy एकदम सेम है. देन दिस बिकम्स, इसको इससे कंपेयर करेंगे. Look, the right hand side is here is identical to the right hand side of this. We can equate the left hand sides. So now this becomes this equals this. Step 6 is to convert the shadow curve integral back to the 3D curve. Recall gxy is this. Evaluating fx using the surface z value at each xy. When you walk along the shadow curve c in the flat xy plane using g. Where were I? Wait. So recall this, evaluating fx using surface z value at each xy. When you walk along the shadow curve c in flat xy plane using g, it gives exact same numerical value as walking along the real 3D curve c on the surface and evaluating fx dx there, because xy values match point for point for between c and c. That's literally what shadow means. Dx doesn't care about z at all. I did not understand this part. फिर से देखती हूँ एक बार. एक मिनट. स्टेप 2 समझ आ गया था. हाँ, स्टेप 2 में भी कंफ्यूजन है, राइट, थोड़ी सी. And then step 6, recall this equals this, evaluating fx using the surface g is xy and what do you mean? I don't remember actually. Function in xy and that, what is this? Step 6 नहीं मुझे समझ आ रहा. खैर, so we were here, right? This is equal. So now इसको इसमें convert करना है. So now g dx become fx dx. Step 6 not clear. Combining step 5 and 6, part A is done. I did not understand part 2 and 6. Step by part है. Step. So part B and C, same proof, different letters. If instead you project onto xz plane, shadow looking from side along y-axis and repeat step 1 to 6. So fyj instead of fxi cap, you get by identical logic this thing, and then this while projecting on yz plane. I'm not really deriving these on screen because if it is letter for letter the same 6 steps. Just cycle x to y to z to x throughout. Okay, For your recording, you can say by symmetry. Okay, guys, by symmetry. Examiners accept this. So final step is to add all these three parts. Add all three parts together. So now we are going to add. To get this, we are going to add all of these for x, y, and z. Both sides, we are adding both LHS and RHS for both of all of these three equations. So left side, since curl is built from ordinary derivatives which are linear, ordinary derivative, curl is built from ordinary derivative. What do you mean ordinary derivative? I don't know. So the left side combines into this. ठीक है अभी के लिए. Right side from section 1.3. So the right side combines into this, and the right side fx dx fy dy fz dz becomes this fdl. So the right side combines into this. Therefore we have our formula proved. Please explain again. What was this? So पहले हमने लीनियर इंटीग्रल लिया अराउंड अ क्लोज लूप. वी प्रूव द थ्योरम. मुझे तो याद भी नहीं है यार, दोबारा से देखना पड़ेगा. वेट. So first we are going to use this curl formula, Green theorem, to prove this. For the proof we are going to compute curl first. So for only fx, these are going to be 0 in the curl formula. From the curl formula we got this. Then express NDS in terms of xy. Very complicated actually. Re-explaining step 2 and step 6 and the final steps lower with pictures and words. ठीक है. So step 2 revisited, we have NDS equals this. ठीक है. So what the hell is this? Should I mention what I want to know? Simpler. Okay, so in step 2 I was confused about how we got this. Step not understand. Step 6. Step 6 was completely unclear. I couldn't. And final part में what was difficult? Ordinary derivatives. And right hand side I guess was easier. Let's see. 41 minutes already. I'm tired. Let's slow down on those three parts. Re-explaining step 2, the pull out two pieces part. So remember when what a dot product does. If you have two vectors written ijk form, the dot product only multiplies matching components together and adds them up. So we have a dot b, then ax bx, ay by, and az bz. Okay, az bz. Uh, okay, so the I cap part of A only ever multiplies I part of B. Same for J with J and K with K, they never cross multiply. Now look at what we are dotting together. I part is 0, we have J and K. Notice the I part of this vector is 0, there is no I term at all. We have the general formula as this. When we dot these two together, because dot product only matches same letters, I part of first vector, which is 0, times I, so this becomes 0. I part of first vector is 0, I part of second vector contributes nothing since 0, anything times 0 is 0. Okay, J part of first vector times J part of second vector. Let's see. So this times this, but we were not doing it. Like, were they doing this? I don't know. Okay, so we literally don't even need to write the I part of NDS. It's going to get multiplied with 0. That's all. Pull out just the two pieces we need, means don't waste writing J matching piece to K. So J dot. But why did you how did you bring J to this side? What the hell is going on? NDS equal to both of these. Then how NDS become equal to this and this separately? I don't even know what I'm trying to ask, but I don't know what the math is going in there. Re-explaining step 6 with real numbers this time. Let's make this concrete instead of abstract. Was step 2 clear? No. This was the step 2. So step 6. Picture surface z equals xy, just a made up example surface. Let's make this concrete instead of abstract. Picture z equals xy, just a made up example surface. Take one example. There, so this point sitting on real 3D curve C has coordinates 1, 2, 2. Now project straight down. I don't know. Because g was defined to be fx, but with z replaced by surface z's value, so evaluating g at the shadow point xy gives you exactly the same number as evaluating fx at the real point xyz on the surface, because the surface point z value is precisely related to xy, which is what we substituted into g in the first place, and dx is identical to, as you move along c, your x coordinate changes by some tiny amount dx. As you move along shadow c at the corresponding point, x changes by the exactly same dx. Dropping z doesn't touch x at all. Dropping z doesn't touch x at all. What do you mean? Anyway, so term by term, point by point, g dx computed on the flat shadow curve and fx dx computed on a 3D curve give identical numbers at every corresponding point. Add them up all along the whole loop and the total must match too. It's still not clear. Re-explaining the final step. Fine. Let's see. What was the final step? Okay, I was asking कि ordinary derivative क्या है और ये कैसे related है. Let's see. What linear means in plain, and an operation is linear if doing it to a sum gives the same result as doing it separately, then adding and then adding. You already know one linear operation. Okay, ordinary differentiation, please check. Same answer either way. Differentiation distributes over addition. That's what linear means. Why this matter for curl is built entirely out of partial derivatives, nothing else. So if you feed curl a sum of vector fields, it just distributes exactly like the example above. Why do we care? Because our whole proof strategy was to break f into 3 separate pieces, then prove for theorem for each piece separately, then just add the result together. That just add the result together step is only valid because curl is linear. If curl did not distribute over addition, then knowing the theorem works for each individual piece would tell us nothing about whether it works for the sum. Fine, let's try to make sense of what happened. Let's start. So we need to prove this. So to prove this, we have this geometry. We are taking a 3D surface as floating in 3D. Then we are like putting light onto it to get a shadow in xy plane, right? To get a 2D shadow, 2D region. in the xy plane. Fine, since we want to show this, let's first take curl of fx. We are going to use the formula for curl, and since we if we pretend fy equals 0 and fz equals 0 everywhere, but why are we pretending? Acha, because we only want to take for fxi. We only want to take curl for fxi for one part, right? So we are going to pretend fy and fz is 0. So उसकी वजह से this would reduce to this equation. Then हमें मिल गया है कर्ल. वी आर गोइंग टू फाइंड आउट NDS. उसके बाद डॉट प्रोडक्ट लेंगे दोनों का. देन दिस इंटीग्रल, सरफेस इंटीग्रल. ओके, सो नाउ NDS के लिए इन टर्म्स ऑफ dxy. सो दिस इज़ अ स्टैंडर्ड ज्योमेट्रिक फैक्ट, तो ये याद करना पड़ेगा, राइट? अब why does this make the surface bar perfectly horizontal? From this, pull out just two pieces we need, matching step 1, which only at J and K. So J के साथ डॉट प्रोडक्ट and K के साथ डॉट प्रोडक्ट ले रहे हैं ना. आई डोंट नो इसका आई कैप किधर चला गया यार. इसका J कैप एंड K कैप, सॉरी J कैप एंड K कैप इधर मल्टीप्लाई हो रहा था, उधर जाके डॉट प्रोडक्ट कैसे बन गया मुझे नहीं समझ आया. ठीक है, आई थिंक आई विल मेमोराइज दिस, या मे बी आस्क चैट GPT. I'm going to take a screenshot actually. ठीक है, somehow let's just मान लेते हैं कि ठीक है, यहाँ से हमें ये दोनों मिल गए हैं, NDS and KNDS, J NDS and KNDS. नाउ वो दोनों का डॉट प्रोडक्ट लेना था, राइट? सो वी वांट दिस, सो वी आर गोइंग टू टेक डॉट प्रोडक्ट with both of them. दोनों अंदर जाके मल्टीप्लाई टू बोथ ऑफ आर वैल्यूज that we got. एक मिनट, what the hell? रुको. We got this for J and this for K, and this is for J and this is for K. तो हम बस उसका रिस्पेक्टिवली ही मल्टीप्लाई कर रहे हैं, ठीक है. वी टुक दिस, I don't know, it's dot product or simple multiplication, whatever. So this is written like this, and dx dy बाहर ले लेना है, then हमें ये मिल जाएगा, and this looks like another formula from chain rule. So here we have it from our tools. So now by using this we can like क्या बोलते हैं, reduce it to this. So now this thing can be reduced to this, right or not? dx dy only अंदर का reduce होगा ना, ये इक्वल हो जाएगा माइनस के f सॉरी कर्ल g 1 कर्ल y dx dy. ठीक है, ओके. Now we are going to integrate both sides over the surface and apply Green's theorem. अब ग्रीन थ्योरम कैसे अप्लाई हुई है इसमें? ठीक है, दोनों तरफ इंटीग्रेट किया है. सो यूजिंग ग्रीन्स थ्योरम, ये आर्बिट्रेरीली हमने लिया है या ऐसे, आई डोंट नो. सो वी टुक P equals G and Q equals 0. Another thing to remember. Then we get this, and this looks similar to okay. हमने ऐसा इसलिए किया ताकि हमें ये सिमिलर मिल जाए. अब ये हमें सिमिलर मिल गया है तो ये आगे का भी दोनों इक्वल होगा. सो नाउ दिस टू आर गोइंग टू बी इक्वल. अब इन दोनों को इक्वल रखा हुआ है. एक मिनट. नहीं, इन दोनों को इक्वल रखा नहीं हुआ. इसकी जगह पर, क्योंकि ये दोनों इक्वल हैं इसलिए इसकी जगह पर ये सब्स्टिट्यूट किया है. ठीक है, टू गेट दिस देन कन्वर्ट टू 3D में कन्वर्ट करने के लिए ये वाला मुझे समझ नहीं आया था. एक बार फिर से देख लूँ क्या. Recall gx equals this. Evaluating fx using surface z value at each this. When you walk along the curve c flat xy plane using g, it gives the exact same value as walking along the exact same value as walking along the 3D curve c on surface of dx. Walking along the real 3D curve C on the surface evaluating fx dx. There xy value matches point for C, and C, that's literally what shadow means, and dx doesn't care about Z at all. So G can be replaced with fx. ठीक है, मुझे याद नहीं है कौन से वाले से रिकॉल करा रहे हैं. विच पार्ट, कौन से पार्ट में था ये. देख के याद आता है. रुको, चेन वाले में था शायद. सो हमारे पास है z इक्वल्स एफ एक्स वाई. So we are trying to say कि we want to show the change in f, function f, when with y, right? How y affects fx. Then either we can check directly for fx, right, or we check for fx z की वजह से कितना चेंज हुआ, then z y की वजह से कितना चेंज हुआ, to get this. बट ये कैसे रिलेट हो रहा है. इसमें g कहाँ है. g तो है ही नहीं इसमें. एक अलग फंक्शन, वटएवर, एक और चीज़ याद करने के लिए. So g would be replaced with fx. Now we have this. अब ये fx के लिए आ गया fy, और fz के लिए भी लिख देंगे. एंड देन वी आर गोइंग टू ऐड लेफ्ट हैंड साइड्स एंड राइट हैंड साइड्स. लेफ्ट हैंड साइड्स एंड राइट हैंड साइड्स. एंड राइट हैंड साइड्स के लिए एक और वही वाला फॉर्मूला यूज़ होगा. दिस इज़ गोइंग टू बिकम FDL, कर्ल ऑफ FDL. नहीं, कर्ल नहीं, जो भी है, क्लोज्ड इंटीग्रल ऑफ FDL. एंड ये वाली साइड बन जाएगी कर्ल ऑफ FNDS. ठीक है, आई कैन मेमोराइज इट थोड़ा बहुत करके. I think I would need to memorize it because this is one of the most important topic in this paper. This is highly predictable and this comes almost every time. There are a few things that we would need to memorize. Let's do a quick revision. Topic.